All right, we are starting the final chapter for step 2, and it is chapter 14, and we are covering the topic of multiple linear regression. So, last chapter, we estimated the linear regression model, yi equals beta naught plus beta 1 xi plus epsilon I. That is, we just had a regression with one explanatory variable. We had one dependent variable, or one response variable, we called it y, and we had one explanatory variable, and we called it x. Our goal was to see, can we explain variation in y from x? Can x make predictions about y? If it can, then we find coefficients, beta naught, the intercept, and beta 1, the slope coefficient, and we use those to estimate values of y, the response variable. But in this chapter, so chapter 14, we're going to be estimating linear regressions with two or more explanatory variables. So we'll focus mostly on just two variables because this chapter 14, I don't want to go into a ton of detail. We're going to go through it at a fairly high level. So we mainly want to be understanding the concepts and the definitions more than anything. But in the linear regression, multiple linear regression, you can add as many variables as you want, so long as your sample size is bigger than the number of explanatory variables. But like I said, we'll focus on just two explanatory variables. So let's take a look at our model. Should look pretty similar. So now we have yi is equal to beta naught, our intercept, plus beta 1 times x1I, plus beta 2 times x2I, plus epsilon I. So instead of just having the one slope coefficient, beta 1, and the one x variable, we now have two slopes and two x variables. So we have two explanatory variables, x1 and x2, and each of them have a corresponding slope coefficient, beta 1 and beta 2. Beta 1 is the slope coefficient between x1 and y, and beta 2 is the slope coefficient between x2 and y. As usual, beta naught is the intercept, and epsilon is our unobserved randomness. So I basically copy-pasted these from the last chapter. So yi is just the response variable for observation I. And then x1 and x2I, so these are explanatory variables. So for observation I, so let's take observation I or observation 6, for example. We have a value for both x1 and x2. So these are our actual observed data. So whenever we open Excel, this is the actual data that we're working with. So beta naught, this is our y-intercept, and it's the same interpretation as the last chapter. The only difference is that now we're saying it's the value of y when both x1 is 0 and x2 is 0. So sometimes that has an actual meaning, sometimes it doesn't. Depends on the context of our problem. So beta 1 and beta 2. So beta 1 is the slope of y with variable x1 holding x2 constant. And that's an important idea. The slopes of each variable are only with respect to that actual variable. So for beta 1, we're looking at the slope between y and x1. We're essentially ignoring x2, which is why we need to hold it constant. We're saying if x2 is not changing, this is how y changes with respect to x. So another way we could say it is that the change in y per unit change in x1 holding x2 constant. So we're really just adding that extra stipulation to our interpretation. Okay, so beta 2 is essentially the same thing, is that it's now the slope of y with variable x2 holding x1 constant. So again, how is y changing with respect to x2, assuming x1 is not changing? So another way we can say is that it's the change in y per unit change in x2 holding x1 constant. So epsilon I is the exact same interpretation as before. It's just random error in y for observation I. So it's just unobserved randomness. Any process, generally speaking, is going to have some inherent randomness involved, and we're not going to understand that, which is why we call it randomness, and that is incorporated into the model. And then finally, I equals 1 to n, just meaning we have n observations in our data set. So far, this should be very similar to what we covered in the prior chapter. But again, I'm going to leave these two things highlighted. In the prior chapter, we had one explanatory variable. Now we have two or more. So just as before, we're going to estimate our population coefficients, beta naught, beta 1, and beta 2, with our estimations, or our sample statistics, b naught, b1, and b2. So the true parameters are the betas. What we're actually estimating with our data are the b's. And so our regression model, this is exactly what we saw above, yi is equal to beta naught plus beta 1, and so on. So this is going to be estimated by this. So we have yi hat. So again, y hat means predicted value of y. So just recall y hat is predicted value of y. And it's going to be equal to b naught plus b1 x1i plus b2 x2i. Okay, so let's just look at an example. So for this chapter, we're going to actually calculate all of these things in a very straightforward manner in Excel. We're going to pretty much just press a button and get some Excel data. But I went ahead and just grabbed one of the problems in the textbook. So this county is located approximately 25 miles east of New York City. The data is stored in this data set. I'll have it posted in our Excel lab folder for the week. So we have data on the fair market value in thousands of dollars, land area and property in acres, so land area, and age in years for a sample of 30 single-family homes located in Glen Cove, a small city in Nassau County. So we want to develop a multiple linear regression model. So let me clean this up so we get the main idea. We want to develop a multiple linear regression model to predict. We want to predict fair market value based on land area of the property in acres and age in years. So we'll do this in the Excel lab for the week, and I just have our coefficients listed right here. And so the first thing we want to do is let's just go ahead and write out our model. So we could say y I hat is equal to 532.288 plus 407.135 times x1. I could do x1i plus, and actually it's a negative because we have a negative coefficient, minus 2.826 times x2i. So if we wanted to convert this into words, I would say, so this is market value. So I would say value hat, right? It's hat because it's predicted. So the predicted value is just going to be equal to 532 point, I'm going to just round, 0.3 plus 407.1 times property size minus 2.8 times age. Okay, so let's go ahead and dissect this. So our B naught is 532. So if we were to interpret this, we would say that the value of a home that is 0 years old with 0 property size is $532. Let me say $532,000. Now we might say doesn't make much sense, right? Doesn't make much sense because a home needs non-zero property size. Right, as far as I know, for a house to actually exist, it must have some amount of property. So if property size is 0, that means there is no home there. Okay, let's move on to B1. B1, we'll say, is 407. So that's for property size. So for every acre increase in property size, value increases by $407,000. Then let's not forget our extra stipulation, holding age constant. So that's saying if two homes that are of the same age, if one has an extra acre, it should be worth about $407,000 more. Okay, B2. So we have minus 2.8. So we could say for every year older the house value decreases by minus $2.8,000. And actually saying decrease by negative doesn't make sense. I'm already saying decrease, so it decreases by $2.8,000. Holding property size constant. Okay, so we said B naught maybe doesn't make a ton of sense just because there's no such thing as a house with 0 property size. But we can think about the other coefficients just in terms of do they make sense. So does it make sense that this is a positive number? Well, yeah, the more property you have, the more it's gonna be worth. And age, I actually don't know if this one makes a ton of sense to me, because we know that, barring the financial crash of '08, historically homes always increase in value. But we can also see the effect size is much smaller. This is just 2.8. This is 407. So we'll see. It might not actually be statistically significant. We will look at that later. But let's go ahead and also do a prediction. So let's do a prediction. So prediction of value when, let's see. I should say, I'll just say when property size equals 0.25 acres and age equals 55 years. So all we need to do is plug into our equation here. So I'd say value hat. So we would have value is equal to 532.3 plus 407.1 times property size. So we just said property size is 0.25, so let's plug in 0.25 minus 2.8. Our age is what, 55? So 55, which gives us a value of 479, and our units are in thousands of dollars. Okay, so a home with a property size of a quarter acre and 55 years, we would expect that to be worth about $479,000 in this county.